Hello, everyone. I'm glad to introduce our work, Transformer3D-Det. Improving 3D Object Detection by Vote Refinement. This work has been accepted by TCSVT. I will introduce our work in 4 chapters. Point cloud is a collection of points in 3D space, which can be used to represent 3D objects and scenes. Recently, with the growth of emerging point cloud-enabled applications such as 3D free viewpoint video, immersive media and autonomous driving, there are several challenging tasks in 3D indoor and outdoor scenes, such as semantic segmentation, detection and more. For indoor 3D detection tasks, the recently most popular method are based on voting process. VoteNet proposed the first voting-based 3D object detection method, which reformulated the traditional Hawk voting process into a point-wise regression problem. There are some variants of VoteNet. MLCVNet encoded multi-level context to promote detection accuracy. HGNet proposed a new hierarchical graph network for 3D object detection. 3DSSD proposed the feature FPS sampling strategy and build a single-stage detector. H3DNet predicted hybrid geometric primitives to enable a better generation of object proposals. However, all these methods ignore the problem of the voting process. Here is a visualization of the voting process borrowed from VoteNet paper. We found that the points often vote to an inaccurate position. In order to better explain the problem, here is another sample of the voting process. The votes are often located at the background, marked in the blue circle, or not tightly gathered, marked in the red circle. The issues hamper the full utilization of input point clouds. To solve this problem, we argue that it is beneficial to exploit rich contextual relations among these vote clusters, as this strategy can suppress clustered negative votes, and Transformer is a good choice. This is the overview of our framework, which consists of the vote generation module, the vote refinement module, and the bounding box generation module. In the vote generation module, the Hawk voting process is used to generate coarse vote clusters. In the vote refinement module, we propose the Transformer-Based vote refinement module with distance-based masked attention to refine the generated coarse votes. Finally, the bounding box generation module generates the final bounding boxes using the refined vote clusters. The vote generation module and the bounding box generation module are the same as VoteNet. For the vote refinement module, we use a transformer decoder-like submodule to generate accurate votes. We use the masked self-attention layer to model local relations among the input vote cluster features and masked cross-attention to learn the complex relations based on both the coarse vote cluster features and the intermediate vote cluster features. Moreover, we refine the vote cluster centers in each transformer decoder-like submodule. By utilizing multiple transformer-based submodules, we can progressively refine the clustered coarse votes based on the relative position of the points in point clouds and generate more accurate vote prediction. We further propose the masked multi-head attention to exploit the contextual information. The inverse distance matrix is added to the initial attention matrix after normalization and masking operation for better spatial relationships. By applying the mask operation, we can effectively learn the attention map at the local region of each object. The loss function of our method is a combination of the detection loss, voting loss and non-vote loss. The detection loss and the voting loss are the same as VoteNet. We propose the non-vote loss to suppress the votes located at the background. We validate our approach on 2 of the most popular datasets. ScanNetV2 is a dataset related to indoor scenes, which consists of RGB-D scans from 1,513 scenes with densely annotated meshes. SUN RGB-D is a single-view RGB-D dataset for 3D scene understanding, which consists of 10,335 indoor RGB-D images. The quantitative results on the ScanNetV2 and SUN RGB-D shows that our method outperforms most methods on these 2 datasets, which validates the effectiveness of our method. The representative visualization shows that our method achieves more reliable 3D object detection results, while other methods may generate much more inaccurate bounding boxes. The visualization of the vote refinement module and not vote loss shows that our method could effectively cluster the coarse votes as well as eliminate the inaccurate votes from the background. The votes of our method can be tightly gathered to obtain better detection results. Here are some other ablation studies of our proposed components. Our method can achieve practical speed up by only calculating the non-zero elements in the sparse attention matrix. Please check out our paper for more details. Our method using localized attention method performs better than standard attention mechanism and different variants. Performance of our T3D framework increase when we increase the number of transformer layers M from 1 to 4. When setting a larger value of M, we hypothesize that there is an overfitting problem on the relatively small datasets like ScanNetV2. In conclusion, in this work, we propose a simple and effective transformer-based framework with a newly distance-based masked attention mechanism. With the aid of the non-vote loss function, we effectively generate more accurate votes and obtain the SOTA results. The qualitative and quantitative results validate the effectiveness of our method. After our article was submitted, several transformer-based methods are proposed in ICCV 2021. The group-free 3D method proposed a sampling method to generate initial object candidates and stacked attention modules to extract and refine object representations from all points. However, their method performs much slower than normal voting-based method. The 3DETR method proposed an end-to-end transformer-based object detection model for 3D point clouds, which does not rely on 3D backbones such as PointNet++ and uses few 3D-specific operators. However, their methods achieves relatively poor performance. I hope our article will contribute to the future development of the community. Thank you for your attention.